Hello everybody. This is take 3 for me because I talked through for about 5 minutes and I did not push record. So just want to introduce the 3 different types of energies, the mechanical energies that we're going to look at, mechanical being the energies of motion, and talk about the conservation of energy very quickly. So the first type is going to be kinetic energy, which is usually just shown as a K. All right, so K is equal to 1/2 mv squared. So the amount of energy of a single object, so the mass of that object won't change, is solely determined by the speed at which that object will be moving. Now, of course, if we took 2 different objects that have 2 different masses, we can have them move at different speeds so that the kinetic energies of those 2 objects can be the same. All right, but for one object that is moving in a scenario, the kinetic energy basically just depends on its speed. All right, the next type of energy is gravitational potential, which is usually U sub G. You can also write that as PE for potential energy, and that also can apply up here with the kinetic energy. I'll kind of flip-flop between them. All right, so the potential energy only depends on the mass of the object, what planet you're on, which is G, and then the height above a reference point that the object is. So if I take an object and I raise it up to some height, and I decide that I want the lowest point here to be my 0 meter height, that means as we move upwards, we're going to end up with some positive value for that height. Now we can take the same object, but make the highest point our reference point of 0 meters, and we would still end up with a height here, except this one right here would be a negative height. We'd get the same answers no matter which reference point we choose, but it is arbitrary and you can choose it yourself. Sometimes once you get used to solving problems, there's a way that you can pick the easier reference point for the problem. All right, the last type is spring energy or elastic energy, and it is a form of potential energy, and it depends on what the stiffness of the spring is, which is K, and then how far the spring is either stretched or compressed. All right, spring constant has units of newtons per meter, and then the distance is, of course, meters. Again, spring constant is basically how stiff the spring is. Large spring constant, much more difficult to stretch or compress. All right, so these are the 3 forms of mechanical energy, which is the energy of motion that we're going to be looking at. The next thing to define is going to be capital E, which is the total mechanical energy. And that should make sense, that it's going to be the sum of the forms of mechanical energy. So the total mechanical is equal to the kinetic plus gravitational potential plus spring potential at any point in the scenario of whatever the object's situation is. And when we start with conservation of energy, the idea is that the total mechanical energy at some starting point has to equal the total mechanical energy at any other point. So written out long ways, it could be that there's kinetic plus gravitational potential plus spring potential at the starting points has to equal the kinetic plus gravitational plus spring at any other point. Now, you will 99.9% of the time never have all 3 types of energies at a location. Almost always it's going to be 2 types. at a time. So we can create a scenario here where maybe there's a block attached to a spring here, and the spring is compressed some distance x and is stationary, so that at that starting point, the total mechanical energy is simply equal to the spring potential plus the gravitational potential, because it has no speed. So one of the things you want to do is maybe ask yourself 3 questions. Is it moving? Does it have a height? Is there a spring? All right, so there is a spring, so we have the spring potential. Does it have a height? It is above some reference point, so it does have gravitational potential. Is it moving? No, it is not. So we don't have the kinetic. And then we look at maybe some ending point here. So now it has gone down the ramp. It is now moving with some speed, all right, and it's at the lowest point. So the final mechanical energy at that point, is it moving? Yes. Does it have a height? No. Is it touching a spring? No. So here is our conservation of energy equation. The next step that would happen in that type of problem solving would be to substitute in what the individual equations are for those concepts. So we would have the spring energy, which is 1/2 kx squared, plus the gravitational potential energy, which is mgh, and those are at the starting point, and that's going to have to equal the 1/2 mv squared for the kinetic energy. And usually it's from that point where we'll start to solve for whatever the problem asked for. After this video, I want you to look at some solving problems for conservation of energy, and then after that you're going to get into something called work, which is where does this energy come from? And it's the application of a force to an object that actually puts energy into the system or takes the energy out of the system. And really the form of energy that's going to take it out is going to be the energy that is lost due to friction, which is actually going to be in the form of heat, because we know that friction is when things rub together and that generates heat. So it's going to actually take the mechanical energy and turn it into heat energy. Now, I want to just show this quick app here. We'll see if it actually works out. And it's working. All right, so we have a skateboarder that's going along a ramp, and just some things to point out. On the right-hand side, there's a slider that says friction. That is down to none. All right, the gravity is that of Earth's, so this skater is on planet Earth. And if we look above the skater's head, there is a pie graph that is constantly changing, and it goes from all blue when it's at the highest to all green at the lowest. And if we look on the left-hand corner, you can see that it's just identifying what forms of energy exist at those locations. But the total mechanical energy is always the addition of both the blue and the green as the skater is moving through. So the total is never changing. It is only changing form from the gravitational height energy to the moving energy. So it's at rest when it's at the highest point. All right, it has no height when it's at the bottom point, so it's going to be moving its fastest at the bottom. If we do add friction, let me see if this will let me do it. And it will not. All right, so if we added friction there, of course you would know that the skater would stop going to the highest point. And one more thing we can look at is if I can put a reference line. Oh, that worked. I can raise this up to where the skater reaches there and over there, and it always returns to the same height no matter what side it's on. Even if we change the shape of the ramp and made this side, can't stretch that one out. Can I stretch this one out? I like to talk to myself. All right, but it's not letting me change the friction or add that stuff anymore. Hopefully you get the idea, and even the pie graph disappeared. So that's just, again, simple conservation of energy, and the problems actually aren't that bad. So hopefully when you watch that next video, you think the same thing.